Hello.
Hey, how's it going, everyone?
Hi, everyone.
Let me know if you guys can hear us okay. It's great to meet you all. Let me see. Give us a quick thumbs up or a yes in the chat if the audio is okay from both of us, real quick.
Loud and clear. Thank you, Tom. We can hear you.
Perfect.
Perfect. Great.
Amazing.
Yeah, Olga has already asked if we're sharing the recording. This is being recorded. We will send out a link to the recording after the cast is done. It'll go to your email.
Perfect. Yeah. Can everyone drop where they're currently actually watching this live stream from? I know we have seen some messages earlier, and it looks like we have people from all over the world, so that's awesome. UK, nice. Phoenix AZ, okay, nice. Hey, Donald. Italy, Ireland, wow, okay. I actually just went to Dublin a couple months ago. It's great. Denver, San
Andy,
Diego.
did you get people to sign up in person? You were recruiting them to
Yes, I
on
was
your
walking around the
travels?
streets for sure, for sure. Houston, Vancouver, that's a great place. Wow, okay, so we have everyone from all over the world. That's awesome. Munich, Germany. Great. Should we go ahead and dive into the live stream, Annie?
Yeah. Maybe give it another minute or so. I see the number of people joining is still increasing. So yeah, if you want to get
Perfect.
those slides up, I think we can start in about a minute.
Sounds great. Dallas, Texas. That's awesome.
Wow, people are from all over. A
Yeah.
global live stream.
Love it. Let me go ahead and just get everything all ready and we can get started shortly. Awesome. Let me know if everyone's able to see my screen all right.
Looks great to me.
Perfect. Actually, what I'll do, let me stop my screen share. Awesome. I think we can go ahead and get started. And if anyone wants to trickle in while we start, more than happy to do so. So let me share my screen with you all again. Awesome. Looks like we have the wrong screen.
Nick, yes, this session is being recorded. The link will get sent out afterwards.
Awesome. Okay, well, welcome everyone. We are stoked to have you for our live stream today. Today, we will be talking about one of the applications that Annie and I built called Vibe Check, and also be going more in depth regarding how you can create a multimodal music search application with AI. And so we'll be doing a quick little overview over all these topics. We'll show you a demo and we'll give you a full in-depth walkthrough of how we created this. And so if I go into the agenda real quick, we'll just do a quick round of introductions. You can meet the speakers. And then we'll do a background regarding vector search, multimodal models, how they work hand in hand with one another, so on and so forth. And then we'll dive into the demo and go through the walkthrough. And lastly, we will do a Q&A. But we want to keep this as interactive as possible. So if you have any questions along the way, feel free to drop in the chat. We'll be monitoring it during the entire time. And we'll just stop intermittently and answer any questions along the way. And so let's get into it. So meet your hosts. I'm currently Andy Gadraw. I'm a solutions engineer here at DataStax. I've been with the company for a little bit over a year and a half now, based out of Phoenix, Arizona. And I work very closely with Annie, which I'll let her introduce herself real quick.
Great. Thanks for doing the intro, Andy. My name is Annie Fan. I am a lead solutions engineer for DataStax. I actually joined like just a month before Andy, so we've been at the company for about the same amount of time and have worked on the same team for like the entire time we've been part of DataStax. So yeah, I thought it was really cool that we got the opportunity to run this live stream together. It's like not something we typically do. We came up with like this idea for a demo and something that we wanted to showcase that we thought would be pretty cool to show folks. I'm based in Chicago, Illinois. Been here for a number of years. And I wanted to get a little seasonal and topical. Halloween is coming up. This is going to be like Hollow Weekend, most likely, unless people want to celebrate November, which, to each their own. But I'm going to be celebrating Halloween this weekend. If people in the chat could share, do you have any favorite Halloween candy? What do you think is the best treat? I'm a sucker for a Twix because
Oh man,
I like the chocolate, the crunchy, the texture. So good.
love it. It's honestly hard to kind of choose one, but I will have to say I'd have to go with Reese's. Anything chocolate and peanut butter is, man, that's my go-to. Anytime I get it, it never stays in the house for longer than a couple of days.
Nice. Yeah, I see Michelle likes Haribo gummy bears. That's a
Love
hot.
those.
I feel like it sticks to the teeth, so I'm not into that. Pumpkin shaped candy bars, Snickers,
Snickers.
candy corn.
Oh
It's
man, it's
all
too
good
early.
though.
Yeah, for sure. It's too early for me to be hungry for candy. Oh goodness.
As long as it's got sugar, that's fine. That's fine
For
with me.
sure.
Cool. Okay.
Awesome.
Thanks for sharing. We can move on.
For sure. Yeah, let's dive into it. And so today, majority of this live stream will be talking about our demo called Vibe Check. And how we came about this project was Andy and I were sitting down one day, and we're two music fanatics. We love music. However, we can never choose the right song for the right moment. We have tons and tons of playlists, but whenever we're driving or working out, we can never find that right song for that right moment. And so we decided to try to solve this issue by building this demo called Vibe Check, which is essentially a song recommendation system where a user can put in their current setting, either a description or a picture of what they're doing. And then essentially songs from their playlists on Spotify would be recommended to them to play in that exact moment. And you kind of see a little, quick little screenshot of it right here on the right-hand side. And we'll be, kind of doing the full demo, but also talking to you regarding all the different components that went into this. And so we primarily used Python to build this application. So when we link the GitHub repo and all things like that, it is all built in Python. And then for the front end framework, we use Streamlit to essentially have all these button text boxes and display the application to the user. And then you see here, we use Spotify. Obviously, Vibe Check, we wanted it to integrate with our Spotify playlists. And so we use the Spotify API to get all that information. And then we also use OpenAI, specifically two different things from OpenAI. We use their GPT-4o for our LLM on the back end. And then we also use their text embedding 3 small model to generate vector embeddings of our song data. And then lastly, we used AstroDB as the main vector database to perform these similarity searches on the back end. And so I know I kind of just ran through a whole lot of things there, but we will go far more in depth into each of these things shortly and show how they all interwork with one another. And so one thing to keep in mind as well is that Vibe Check is a demo. It's not necessarily a full production grade application. So keep that in mind while you're playing around with it, while you're testing. This is just meant for demo purposes.
Yeah, we
And
built this over the course of like a week. Like we spent a couple days on this, so it's very like proof of concept sort of thing. And we were basically showcasing what you can do with like multimodal and with vector databases. So yeah, just for full context there.
for sure, it was just Annie and I hacking away at it for a couple of days. So. And so to kind of set the scene, we can talk a little bit about vector search because that's what's going on the back end with our database to essentially perform these similarity searches. And so one question that comes to mind is, what even is vector search? Well, essentially, it's a method of finding semantically relevant information from one another. And we can convert this type of data text, images, audio, to something called embeddings, or a long list of numbers. And this is a one-to-one match with the piece of data. That way, when meaningful embeddings are stored within like a vector database, like AstroDB, for example, we can search for similar unstructured data without having to rely on keywords or structured filters. And so that's kind of the core backend framework for this application. A really cool example that I like to think about is, hey, let's take the fruit apple, for example. Well, you can see here that the vector embedding in this 300 dimensional space here is somewhat over here. But if I were to take the fruit banana, right, it's going to be mapped or plotted very similar to apple because they're semantically or contextually relevant to one another. And that way, when I take the company apple, which you see right over here, it'll be stored a little bit further away than apple and banana because it doesn't really have the same semantic meaning or contextual characteristics of our fruit. And so you can see here that the company Apple is actually closer to the company Google, and they would be kind of returned within the same vector or similarity search. And so that's really what vector search at the end of the day is. It's really good for taking unstructured data and finding similarities between one another. And with that being said, we can maybe dive into a little bit about multimodal models, and then we'll get into how vector search and multimodal models kind of work together with one another. And so what are multimodal models? Well, in the AI space, how I like to think about it is a mode or modality is essentially a type of data that we can either use as an input or an output to a Gen AI model. And so what you see here in this diagram is we can take things like text, images, audio, video, so on and so forth. And we can either, build this knowledge base or insert it into our Gen AI model and either, use it as an input or retrieve output from it. And these multimodal models allow, these Gen AI models to essentially have a broader, characteristics of our data and understand, a better definition of our knowledge base. So what are examples? Well, LLMs, for example, we have some, ChatGPT, Bard. There's a variety of different multimodal LLMs that are provided out there in the world that we can use. Secondly, our embedding models. We have OpenAI's ADA002 model, NVIDIA's Embed Q&A model, so on and so forth. There's tons of embedding models out there in the world that we can use that are multimodal, capable. And then lastly, our diffusion models. We have Stable Diffusion, DALL-E, et cetera, and all of these fit under this umbrella of multimodal models.
Great. I'm going to pause you for a second for a question. So someone's asking, so the word apple could appear several times in a vector database?
Yeah, for sure. It could, depending on how you structure your database, you can either have only just one, one piece of data stored within the database, or you can have apple multiple times. It's really up to you, but it's more for that vector search part, where if you were to search for something like a banana or another fruit, then maybe, an apple and all the other fruits would be returned back to the user. If there's anything else you wanted to add to that, Annie.
Yeah. I think like in this situation, I think the data being stored wouldn't be just the word apple. It would be like apple plus some surrounding context. So the way that you like the only way to get different embeddings for Apple the company and Apple the fruit is if you also have text describing, kind of like giving context on which apple you're actually talking about. So maybe you'd have a sentence that's like, someone plucked an apple from a tree. And then the other sentence would be like, Apple made $10 billion last year. And so if you were doing a vector search for like Apple the company, the sentence that you'd get back is probably related to Apple making however much money instead of the apple getting plucked from the tree. So that's like how like what you're giving to the model allows it to differentiate based on existing context. That's a
For
good
sure.
question.
I think it's a very good point, Annie. Very rarely do we actually embed just a singular word. Usually we actually have something called chunks, which are, a long list of, either a paragraph or a full image and things like that. Things where we have the full context of what's going on, and then we can embed that into the vector database. Any other questions? Let me look over onto our chat real quick. Awesome. We should be good. Great question. And so, right, how does vector search and multimodal models kind of work hand in hand? Well, really, there's two ways of doing this. Method one is we can take a piece of multimodal data, say an audio file, right, and use an audio embedding model, which you see right over here, to generate these vector embeddings, which we can then store into a vector database. And so there's tons of multimodal embedding models that match the type of data, and you can use those. That's kind of like the direct conversion method. It's very simple. But actually, there's also a method too where we use an LLM as a transformer to essentially take this multimodal data, pass it to an LLM for interpretation, and then the LLM will usually spit back some description or its response, and we can actually embed the response given back from the LLM and use that to store it within our vector database. And this is actually what we will be demonstrating. This is what VibeCheck uses. We are not necessarily taking songs and embedding the songs directly. We're actually passing them to an LLM to generate a description of the song and then embed that and store it into AstroDB. But we will go far more in depth into that and actually show you how we've done it via the code. But this method too is usually what we like to do for working with multimodal data.
Great.
And yes, LLM is a large language model.
Sweet. Okay, before we kind of hop into the demo and stuff, I just want to check if all of that context makes sense to folks, if there's any other questions before we dive into it, or if we're ready to just kind of get going.
Mm-hmm.
Sweet. Yeah, let's see the code.
Let's
Here.
do it.
Do you want to? Great. Okay, let me present my screen now. Cool. And then can people see my screen here? So I have slides, I have code, a terminal, file explorer. Sorry, you're able to see? Okay, great. Okay, sweet. So I'm gonna, basically we have this project, this Streamlit project, and we have it as a GitHub repository, which let me actually pull that up for folks if they want to take a look. Great. And then if you wanted to, like afterwards, make a copy of the repo to check out the code and try and run it yourself on your own playlist data, there's full instructions on how to do that in the GitHub repo and some other useful links. But let's go ahead and get this app running. So I'm going to use this command, streamlit run streamlit app.py, and that opens up our VibeCheck demo here. And then would it be useful for me to zoom more, or does this look okay?
It looks good to me, but if folks want us to zoom in a little bit more, we can more than definitely do so.
Okay, I'll leave it unless someone in the chat requests a little zoom. Okay, let's go zoom in a little bit more.
Cool.
Great. Okay, so this is what the UI of the demo looks like. It's kind of split into two sections. So this section is where you connect your playlist and do the ingestion. And this one is where we actually are finding our songs. So this is connected to my camera here. You can actually see a preview of what we can do. But I'll just kind of demonstrate like what that final end result is supposed to look like. So what we wanted to do is to be able to take a picture of our setting and then from that get recommendations of songs that would match that setting. This app is currently connected to a playlist that we created for this demo. So if we want to take a look at that, we've loaded all of the data from this playlist into our Astro database to be accessed by VibeCheck. So here we have 18 songs with a pretty wide variety, some Tame Impala, some Espresso by Sabrina Carpenter, Stronger. We also added a couple of Halloween songs down here. So there's kind of a wide variety of moods in this playlist that might not match, like all of the songs don't match every single situation that you're in. So just to kind of show what that search functionality looks like, if I uploaded, for example, this picture, um, it's it's this one. It's a picture of a bunch of jack-o'-lanterns, very spooky, very Halloween. And then wanted to find songs within that playlist that match this. Here it's running a bit, and then we can see a preview of the image, and then here we see top recommended songs from that playlist: Spooky Scary Skeletons, Monster Mash, Ghostbusters, and those are all three of the Halloween songs that we got, that we have in this playlist. So all of those were returned, as well as a couple of other ones that also have some similarity. So yeah, this is like the result that we wanted. We using this image, we got a recommendation. So let's kind of back up a little bit, and we're going to talk about the architecture of the full app, like what the ingestion actually looks like and what the querying looks like. Um, and here we have our architecture slide where we can talk through that. I do see a couple of questions in the chat. So before we start talking about this, do we want to go through a couple of those?
Let's do it. Yeah, I see one right here saying, what's more efficient? Should we do a direct conversion or through an LLM? Um, any thoughts on that, Annie?
Sorry, let me see the, is it in the Q&A or is it in the chat
It
section?
looks to
In the
be in the
chat.
chat. Mm-hmm.
Direct conversion or through LLM. I think, um, honestly, I think both are useful. It kind of depends on what your use case. In both cases, you would be sending the same amount of tokens to whatever model it is that you're using. Um, honestly, direct conversion might be more efficient because you're only using a model once. Whereas in this situation, we're using a large language model to do one step, which is converting the non-text data into text data. And then we're using an embeddings model for another step, which is converting that text data into an actual embedding. So into that like string, long array of numbers that represents that text. So that's like
Mm-hmm.
two steps of querying models versus if you do a direct conversion, of like taking an image and creating embeddings directly from the image.
Mm-hmm.
But also, I feel like image embeddings models might be like more expensive. They're more specialized, so there's a chance that it might not work exactly the way that you want. But yeah, it kind of
Mm-hmm.
comes down to what exactly you're doing. Anything else you'd add there, Andy?
No, I totally agree. I think both of them are totally fine. It just really depends on the type of data that you want to be stored in the database. So obviously multimodal data, let's take an audio file or an image, for example, right? This has a lot of noise in it where sometimes you don't want to be embedding all those external factors. So for example, if I have a picture of myself, right, that's a piece of multimodal data, maybe I only want to focus on what I'm wearing, for example, right? And nothing to do with my background or what's going on in the forefront of the photo, things like that. That's where you'd probably want to pass it to an LLM to write a description of exactly, you'd give it a prompt of, hey, describe only what the user is wearing, so on and so forth, and then embed that rather than the image itself. Because if you were to do the entire image, all those characteristics of the entire image are going to be embedded. And sometimes you don't want that extra noise, within, your vector database or within your embedding.
Great. Cool. Can the similar logic and principle be applied to videos instead of a Spotify playlist? I would assume yes, if you're, as long as you're able to pass info about the video, so maybe a couple of frames from the video. I mean, a video is just like a ton of images, right? So if you wanted, you could pass all of those images to the LLM and have it do the same thing, or take a couple of snapshots and have it make a guess related to that in order to generate some sort of text data about that video.
Mm-hmm.
And then when you say multimodal, does it have to be diffusion plus LLM? For example, it can't be two LLMs operating in an agent manner. In this case, we're using one LLM in an agentic manner, and then we're using an embeddings model directly on that text. So we're not using diffusion for this example. But if you want to use multiple LLMs to do different agentic actions, that's totally a valid approach. Cool. And then there's a couple more in the Q&A. We could just like burn through those real quick.
Perfect. Yeah. Where does RAG fit into all of this? That is an awesome question. Essentially, where this fits in, this is more of a similarity search that uses an LLM to write a description of the song. We embed it and then search. So it's not necessarily a one-to-one fit with RAG, but it's very easily doable because we can take all the songs that are provided by the database and then feed it back to an LLM for further augmentation. And so I'd say the retrieval and the pre-processing step is very similar. It's a one-to-one match to RAG. All you would need to do is just take that data that's returned from the vector database and feed it to an LLM for further augmentation and generate a response back to the user. And so this might not be 100% a RAG use case, but it's 90% of the way there. We're literally probably missing just one LLM call at the end for further refinement. But in our case, it's not necessarily needed because all of our data is already stored within the database that we need, aka the song name, the URL to it, the artist description, so on and so forth. So there's no really need to have an LLM augment that data. Is that what you were going to say too, Annie?
Yeah, I think that's a great answer. Cool.
Awesome.
Let's So I see there are more questions. I think let's get into the demo a little more and kind of show the code, and maybe that'll answer some of them. And then if we have more time at the end, we can address some of the questions that we missed. But here, yeah, I've had this up for a couple minutes now. This is the architecture diagram. Our app is split into two main functions. One is ingesting the data, and then the other part is querying the data. So ingesting the data, that is what's necessary to do. We need to put everything into a vector database in order to be able to then query it with the user setting images or text descriptions. So I'll talk through how the ingestion portion works. First, we give the application a Spotify playlist ID. In this case, it's the playlist ID for that this vibe check playlist, which is just right here. So we copy and pasted that into our app, sent it to our application, and then using the Spotify API, we got back a whole bunch of song data for every single song that is in that Spotify playlist. So we have the song name, we have the artist name, and then the song ID so that we can serve up URLs that point directly to the songs that we will eventually retrieve. But that's not enough, right? We need some sort of text description and embeddings so that we can do that similarity search when we get the user query. And how do we generate those? We used the OpenAI GPT-4o model to generate the queries. I'll show you the code on what that actually looks like in a second. But the LLM, the large language model, generates text describing the settings that match each song in that Spotify playlist. And then once we have those text descriptions, we send those to AstraDB. Astra actually has this feature called Vectorize where you don't have to create the embeddings manually before uploading your data plus embeddings to the database. You can actually just send the text directly to AstraDB, and we've already set up an integration with OpenAI Text Embedding 3 Small so that when it receives that text data, it converts it to the embedding, all those numbers, and then stores it in Astra all in one step. So that's something that's getting abstracted by this Astra vectorize feature. So that's the ingestion piece of things. Andy, do you want to talk about the querying portion?
Yeah, for sure. The querying portion, or when a user submits their picture or their image of themselves, is very similar actually to what's going on with the data ingestion, minus a few tweaks here and there. And so essentially a user will upload and take a picture of themselves or upload an image into the Streamlit application. And from that Streamlit application, it's actually we're passing this image to OpenAI, GPT-4o model to essentially generate a description of the user setting. And so that's what I was kind of talking to you regarding, using an LLM as a transformer stage where we're not just embedding the image itself, but we're actually telling ChatGPT to, hey, generate a description of the user setting. What are they doing? What are their vibes? What's this? Paint the picture for us. And essentially, ChatGPT will do so because it's a multimodal model. And it will give us back a full description. And we can then take that description, embed it, and perform a vector search using Astra's vectorize feature as well. So that's also, this vectorize, as Annie mentioned, it is, embedding the data being returned back from OpenAI, and then also performing a vector search on the fly together. And so then, once we have that, we have a list of similar songs based off of the user's, setting, and we can return this back to the Streamlit application so the user can, click on it and play the song directly. And so that's the query portion.
Great. Yeah, so that's the full architecture. Let's go ahead and dive into the code now and what it actually looks like. So I'm going to talk about the ingestion piece of things and also show you kind of what the data looks like when it's in Astra. So right now, we have all 18 of these vibe check songs uploaded into our database. Here we can see exactly 18 records in our Astra database. But I'll remove a few of them so that I can show you what it actually looks like when we're doing that ingestion and also talk through the code. So this is just removing a couple songs. Then we're going to dive into this file called ingest.py, which actually does the ingestion. So sorry, did you want to say something, Andy?
Yeah, I wanted to just bring a quick point before we hop into the code. I see a question right here. What is orchestrating all of this? Just custom Python code or LangChain or et cetera, et cetera? Are we using any tools on the back end?
Yeah, so this is a pretty sparse implementation. We're not with it. This is custom Python code. Like we're using Streamlit, we're using AstraPy, which is the client to connect to AstraDB via Python, and then we're using the OpenAI client and sending requests directly to the Spotify API. So we're working directly with all the different pieces that we talked about earlier. I think if you want to add like more advanced functionality and more like decision making that uses LangChain, for example, you could do that. But we kind of went fast and loose with this one and just kind of made the fastest possible implementation that wouldn't require us to like learn frameworks. And it works pretty well. It works pretty well.
Mm-hmm.
Cool.
Awesome. Thank you.
Cool. Okay, so I'll go ahead and talk a little bit more about this code. So when we load the full playlist to Astra, we're calling this function load tracks to Astra given the playlist ID. And I'll just talk through what happens from top to bottom here. So the first thing we do is hit that Spotify API to get all of that song data from the Spotify API given the playlist ID. So if I scroll up to this helper function, get tracks from Spotify, we can see we're literally just sending a request to the Spotify API to get all of that song data. And so this is our like access token. This is the API we're using. And then we get back the response JSON items as playlist tracks, and then we get that returned. So here we're just kind of checking if we've done any of this before so that we don't need to like redo loads of songs that we've done already. And then we're verifying that we did get tracks back from that Spotify playlist. And so that's what this section is doing. And then from here below is when we're actually iterating through every single song, formatting the data, retrieving our descriptions for each song, and uploading them to AstraDB. So this first section here is kind of organizing and pulling out relevant information from that API response. So for each song, we're getting the song name here, the artist name here, and then a song URL, which points directly to the song in Spotify. And we're just kind of saving these as variables to be used later. Here's some stuff for if a song has already been loaded, so we don't like redo LLM calls unnecessarily. But in this case, we hit this block if we encounter a song that is not yet loaded into the Astra database. And so we encounter the song, we have the song data, but we don't have a description for the song. So that's when we call this function called get song description given the song name and the artist name. And so this is pulled out into another helper function right here. And this function uses the OpenAI chat client and the GPT-4o model in order to generate a description of the song. And so here's the prompt that we used. You're an AI agent that helps users determine what songs to play to match their setting. Based on the song name and the artist name, write up a description of what kind of setting would be appropriate to listen to this song. Don't make any assumptions based on the name. Try and use real information about the song to come up with your description. Oops, I accidentally clicked down. So here is the prompt right here. Um, so yeah, go ahead, go ahead.
I was going to say that this is a very important part of the application. This is kind of where we're getting these song descriptions, right? We're generating them through ChatGPT 4o's model, and not just necessarily coming up with them on our own or using a data set that's already provided. We're using the LLM to generate these descriptions.
Yeah. So again, LLMs are not fully deterministic. Like you're not going to get exactly the same description every single time, but we did a little bit of prompt engineering to try and make this reliable to a certain extent. And then after we got back our descriptions for the song, we kind of checked them by eye because they're all songs that we know. And then we saw like, yeah, we're getting good descriptions for these things. So this is where we're generating the song description using the OpenAI LLM GPT-4o. So that is what's happening on this line right here. And now that we have that song description, we can add it as a field to our document. And then this data for every single song in that playlist is getting uploaded to AstraDB right here. So this statement, song collection, insert one document. And here is just kind of some progress tracking to see what that looks like. But I'll show you kind of what that looks like in real time. So I'd already removed 2 songs from the Astra database. If I reload this, I'll see I only have 16 records in here. And the 2 songs that got deleted, if I check my terminal here, my console, Too Sweet and Monster Mash got deleted from the Astra database. So I can try to reload that same playlist again. It should skip over all of the 16 songs that are already in there, but it'll try and reload those 2 that are missing. And we'll see in real time that our application generates descriptions for those 2 songs and then loads them into Astra. So here it's working right now, but we can already see it generated this text for Too Sweet and then loaded it to AstraDB. It's skipping over a bunch of the other ones. And then here for Monster Mash, the LLM generated this text for that song and then uploaded it to the database. So if we come back to Astra and refresh it here, we can see now we have 18 records. All of the songs are now once again in this database and ready to be searched. So that's how the ingestion works for this application. Cool. Yeah, that's what I
That
wanted to show.
that is awesome. Could we actually hop into the database real quick, Annie, and show them the descriptions that were generated by the LLM?
Yeah, that's a great idea. So here we can see all of the fields for each of the songs. We have song name, artist, song URL. So this link would open the track. And then this vectorized field is the text that was generated by the LLM that describes this song. And then this vector is the vector representation of the highlighted text generated by this model, which is this collection is integrated with the OpenAI Text Embedding 3 small model. And the vectorized feature allows us to create these every time we upload a new doc, as long as we say yeah, I want a vector created for this specific field. So that's what it looks like in here. That's kind of what's happening in Astra.
That is awesome. Thanks for walking us through that.
Great.
So yeah, now that we have all of our data within the database, we're able to upload, a user's playlist ID, get all their songs, generate these descriptions of the songs, the LLMs. Now let's, get into the code of how we actually, query these songs. And so we have this query.py file, which we can hop into. And essentially the main part starts here at line 64, where, a user presses the submit button on the application. And so they take a photo, either upload it or use the camera. And once they press that submit button, here on line 67, we're essentially getting a description of the user's, setting. And we're going to this get setting description from image function, which we have defined up here on line 14. And what this does is very similarly to how the song descriptions are made. We are also going to chat GPT 4.0, and we are asking it to, generate a description of the user setting. And so you can see the prompt that we have here. You're an AI agent that helps users find music that matches their current setting. Please describe the ambiance and the vibe included in the image, right? What kind of music would be fitting for, the setting that the user uploaded? What kind of mood is there? So on and so forth. And so a little bit of prompt engineering. And then we're going to the GPT 4.0 model and receiving this, description from, the LLM. And that is what we're using as, the vector embedding.
Great.
And
So,
one,
oh, go ahead,
sorry,
go
go ahead.
ahead. I was just going to ask, like, so this prompt doesn't have any information about what we're looking for, right? So, like,
Mm-hmm.
how does the LLM know, like, what exactly it's supposed to be describing?
Amazing question. So, kind of like in your scenario, right? We had passed the song name and the artist name into the prompt, but here, we're just giving the prompt, we're hard coding it and we're telling it to look at the image. And that's what you see here actually on line 38, where we are actually passing the image of what the user uploaded to GPT 4.0 because it is a multimodal model. It is able to accept images and it can essentially interpret them based off of this prompt. And so we're telling, we're giving GPT the prompt, we're giving it the image, and we're telling it based off of the two, respond. And it's very important to know that GPT 4.0, right, it is a multimodal model. Another example of an LLM that is very capable of doing this is Google Gemini's Pro Vision model. It's great as well, very similarly set up to this. But this is how it knows, we're passing the image rather than, a song name or a artist name. And then we're receiving that description.
Awesome. Cool.
Perfect.
Okay,
And
so
so,
back to here. Go ahead, go ahead.
yep. So great. Now we have the setting description based off of the user's uploaded image. But now let's find similar songs off of that description that, GPT 4.0 returned back to us. And so if we go to this find songs function, which we have, what this is doing is it's going into AstraDB. It's using our vectorize feature to essentially vectorize or embed that setting description. And then it's performing a vector search within the DB and pulling out the nearest matches to whatever the user had uploaded to the user's setting description. And that's what you see right over here. Return the top songs back to the user for them to play. And if we hop into the Streamlit side, we can actually, upload a variety of different images and test this out. So let's try it out. We have a picture of, Annie and I at the gym right over here, one that we photoshopped right before this. And let's see which songs are returned back to us. So if we upload that, what it's doing is it's going to GPT 4.0. It's generating a description of the image that we uploaded. And so you can see this is the uploaded image. We can, toggle the show prompt send to LLM button right here. And you can see that this is what GPT 4.0 returned. It said the image depicts a playful and energetic scene with characters lifting weights, right? Suggesting a workout or fitness theme. These are, songs or, settings that, kind of fit this vibe. A pop, electric/dance, EDM, hip hop, rock, right? All of these kind of fit the same vibe of working out or at the gym. And then if we go down, we can see the best matches that are returned from our database off of the song, off the setting description. And so we have the song name, say Stronger by Kanye West right over here. That seems like a pretty good one. We have the song URL to go play it. We have essentially that vectorized field to say, hey, what is, the song description off of the, GPT-4o. And then lastly, we can also see the cosine similarity score. So how close of a match was this? And we can see here, 0.79 is that cosine similarity or that vector search similarity score. Annie and I were doing some playing around, and we realized that anything above zero point 0.7 is usually a pretty good match to return back to the user. It's somewhat relevant to what they're asking for. And so, great. We have all these lists of songs, and then lastly, we just display this song where you can click on Stronger, and it should open up the URL to play it within Spotify, which is pretty cool.
For sure.
Mm-hmm.
Something that we were trying to implement but didn't end up doing because it just was taking too much time. Like ideally, we could like get a Spotify player embedded into this app and start to play the songs automatically, but we kind of didn't want to spend too much time doing that. So, but that would be like a great next step for this application so that you don't have to like open up the songs on your own. Maybe you could make like a new playlist that only includes songs that have a similarity score over zero point 0.7, and then start to automatically play it for whatever event that you're currently at. So there's like a lot of possibility. If this like becomes something a little more fleshed out, I could see myself using this all day. Like I would hook this up to
Mm-hmm.
my liked songs on Spotify, which is like 3,000 songs long. And then wherever I'm at, I would just take a picture and then have like a 30 song playlist to match whatever it is I'm doing at that moment and have it automatically play. That's like kind of the vision here for what it could turn into.
For
Um,
sure. I
but yeah,
think it's important to note that we are showing this kind of on the desktop application. So it's more for, uploading images right now is what we're showcasing, but you can also run this on your phone and take a picture in real time of what your current setting is and, have those songs play on the fly based off of that. I think that's kind of where the vision of this application, would go.
yeah. How
Hmm.
about we try a few more image prompts, like image or text prompts. So let's see. I just kind of want to see what comes up for these different things. So here I have a picture of a candlelit dinner. And if we try this, hopefully it doesn't recommend Monster Mash. Sweet. And yeah, we see the LLM came up with this description. And then we're getting back songs that kind of match that too. Sweet, Birds of a Feather, Take Five. Pretty accurate there.
Hmm. And the cool part is that we can also not only just use an image to, have this similarity search, but you can also put in a description or type something out and then see where, what's returned from just, a sentence.
Sweet. Do you have any suggestions there, Andy?
That's a good one. Let's try. I always need songs for, a joyride in my car.
Great. Cool. And here we can see this is the full prompt that got sent. There's nothing to generate something based off of. But here we see the first song returned is Drive By. A little on the nose, but honestly, that's pretty good. Riptide. Yeah, I could see myself going on a
Hmm.
road trip to these. That's pretty good.
For sure. I
Nice.
think we need to put this into our actual playlist and give it a try.
Yeah, for sure.
Hmm.
And then the last thing I wanted to show here is just this camera input. So you can see I'm in my room here. We could take a live photo and see what the model thinks is going on. Great. So here's the uploaded image. It's me giving a thumbs up. And here, relaxed and cozy room, casual and positive, calm and simple environment, lo-fi hip
Hmm.
hop, chill pop,
Nice.
casual relaxation, work and study. And that's what we're getting back here.
That is awesome. I
Cool.
think we actually have a couple questions, Annie, that we can maybe answer. I see a really good one right over here, asking if we could re-explain why we are vectorizing the image description sent by the LLM. Do you want to take that one,
Um,
or should I go for it?
sure, I can take it. I think we were looking for something like pretty simple to implement. And also like something that would focus more on the setting of what we're doing as opposed to the image itself. Because if you took a picture of what you're doing and then created an embedding only on that picture, um, the embedding would probably be like a descriptor of like what is in the image. So instead of like saying anything about like the vibe, what sort of songs might be a good match, it would just say like there is a person in a room with headphones on, and it wouldn't give any of that sort of like it wouldn't make any guesses about the ambiance or like what sort of mood that person might be in. So we felt like an easy way to get that information would just be to ask an LLM for that specific information. Like, hey, here's this picture. We're trying to do this with it. Try and give me the most valuable text to do these similarity searches in order to give good song recommendations. So giving all of that context to create data that is hyper specific to this use case, which might not be captured if we were to embed the images directly.
Mhm. Perfect. I think even we had someone in the chat even give their answer to give the embedding more context. That's exactly it. We want to give the embedding as much context as possible, and all the things that we're looking for, right? If we were to just take the image, sometimes it might embed some characteristics such as, demographic, age, height, so on and so forth. These are all things that we don't necessarily want or need for this application, right? And that's why we're going to the LLM to essentially provide these descriptions for us and then embed those so we know exactly what we're looking for and we're embedding exactly what we need. Awesome.
Great. Cool. Any
Any,
other questions here you want to get to?
mhm.
I see in the chat, how do you deal with the subjectivity of the description generated by ChatGPT? Sometimes a song can be considered motivating for someone and not for other people. How can I be sure that my description is generic enough to cover the majority of cases? Someone else responded, you can deal with that via prompts, or you can train a different model. You can chunk and train based on what your version of motivating is. Yeah, if you're trying to make this hyper specific for yourself, you can add criteria to the prompt that says like, this is what I think of these songs generally, and then have the LLM try and apply that to whatever it's getting. Um, if you're trying to keep it more general, then you can explicitly state that in the prompts that you're giving to the LLM. And here, I mean, I didn't tell the LLM to do this explicitly, but it's kind of um, doing that on its own. It's giving 4 different options for types of music or settings that would fit the image. And so there's definitely prompt engineering you can do to kind of fit whatever functionality you're looking for. But then, yeah, training based on how you want the model to behave is also another really great approach.
Mhm. Yeah, I think prompting is kind of the art here, right? Multiple different ways of doing it. You can do it kind of in a very simple way that Annie and I did, where you just kind of, give a good description of what you'd like. But there's also prompting techniques such as few shot prompting, right? Where you actually give examples to the LLM of what you consider songs of motivating are, or scary, or sad, or so on and so forth, right? So the LLM has extra context to know how to classify these groups before doing it. But that really all goes into the prompt. If you really don't want to train, another LLM for this exact use case. Cool. Any
I
other
see
questions?
question on LinkedIn. What technology is being used to get the labels for a given image? For example, Google Vision. So we're using OpenAI GPT 4.0. So right here, we are sending this prompt with the song name and artist name. Oh, given image. My bad, my bad. That's on the query side. We're still using GPT-4o. um, we're sending this prompt, so we're asking the LLM, like we're saying, hey, LLM, we're going to give you an image, and please describe it using this prompt. So that's what's happening. We're using GPT-4o. First, we did actually implement this using with Gemini Pro Vision, but then we decided to switch everything over to OpenAI because we were doing embeddings with one provider and the LLM stuff with another. But we figured if we're using things within the same like universe, perhaps they're trained on more similar data, so you'd get like more consistent results. So, but yeah, you could swap this out for kind of whatever LLM embedding combo that you want.
Mhm. Any other questions that we can answer?
I want to get,
I,
hold on. I just want to get the Halloween example back up. There it is.
awesome. I see here. So this question is, this might be too complicated to answer in the time frame, but how are the distances between individual vectors determined for similarity, and how granular can these be? Well, that's a really good question. There's really three main ways to perform these vector/similarity searches. One of them, or the one that we're using here, is called cosine similarity. And we're essentially finding the distances between the vectors, or how far away they are from one another. And that's what you were seeing when we would show the 0.7, or the cosine similarity scores here all the way on the right of this table. This is being provided by that similarity search, or that metric called cosine similarity. But there's also, a variety of others out there. There's one called dot product, or Euclidean distance. All of these are different ways of calculating distances between vectors and performing these similarity searches. But Annie and I chose to go with cosine similarity. That's usually kind of the de facto, norm when working with vector search. But that's how we do this, and how the
Yeah.
distances are calculated.
Like different embeddings models already by default use different similarity metrics. So if we would try to use this text embedding 3 model with dot product similarity, it wouldn't work well. Like it wouldn't be an accurate representation because the dimensions are, sorry, the vectors are created assuming that like distances are calculated with cosine. So whatever model you're using, that kind of determines what distance metrics make the most sense for it.
Mhm. Awesome. How do you approach training the AI models for different music genres and regional preferences, ensuring that the model understands cultural and genre-specific nuances?
Yeah, that's a really interesting question. So that's not something that we've implemented here. But what I could see happening is if you have user data, and maybe like you want to only recommend certain songs if the user is based in APAC, for example. Like what you could do is add another field here to kind of indicate whether a song should or should not be shown to someone who's searching from APAC. So maybe you could do like the column name would be APAC. It would just be like true or false. And then if you want to limit results for a specific person, when you do your similarity search, you can do something called a hybrid search where you add a filter before you do that vector search. So instead of searching over the entire database, you would say, I want to filter my results to only this subsection of the database where the APAC flag is true, and then do my vector search within that. So that's like a pretty um, like you can add a lot of like variables to that you want to include. If you're trying to do some sort of structured filtering, add more personalization, then there are ways to like add additional fields like metadata, so that you could do that sort of thing. But we didn't implement that in this example. It's all just like full playlist is thrown into Astra. We're searching across the entire thing, but there's a lot of like cool things you could do if you needed to have some more granularity there.
Mhm. Yeah, that's a great question and a great answer. I think that metadata one is a great next step, right? If you already know the genres of the different songs that you're uploading, right? Might as well just use that in a hybrid search to essentially have that as a subset of data that you're recommending. So you know for a fact that, if I'm have some lo-fi songs, right, I can put that as maybe a calming genre or something like that, or study genre. And then maybe have the LLM return, hey, this setting, seems like this type of genre, right? Andy's working. Maybe, put it for study or working genre, and then perform a hybrid search. So you're only, returning or limiting your results to songs in that genre.
Sweet. Cool. Any last questions? I know we're at time now. I'm glad we were able to get through everything and show the code. The GitHub repo for this project is still up on the cast, so if you want to take a look yourself and run it yourself, that's an option. Um, let's see, is there anything else that we want to get to before we end the stream?
I think we should be all good. If they want to maybe use that QR code that we have on our last slide to access that GitHub repo, they're more than welcome to do so.
Sweet. Yeah, I'll pull that up right here. Cool. Yeah,
Hmm.
this was a really fun thing for us to work on, and we really appreciate the opportunity to kind of speak to people outside of the company about like something cool that you can build with AI and with Astra. And yeah, all the code is available, so take a look yourself. If you want to submit issues on the repo or contribute, that's like totally an option. If you want to ask questions about it, there's a link to the DataStax developer Discord where you could join and like message us directly about it or just like talk about things that you're doing. Um, yeah, and if you're building anything cool with Astra, we obviously wanna hear about it. But
Yeah.
yeah, this was a great time.
Yeah, I had an absolute blast. And feel free to fork it. And as Annie mentioned, you can hit us up on the developer Discord. More than happy to chat more about it. If you have any feature requests, things like that. Kind of want to keep this as a collaborative project with everyone, since this is something that Annie and I thought would be kind of cool for us to use at home. And so, with that being said, any questions, feel free to reach out. And we had an absolute blast. Thanks for spending the last hour with us.
Awesome. Yeah. Thank you, everyone. Once again, this is recorded. The link will go out as soon as it's ready following the cast. And yeah, reach out to us whenever you want with any questions you have via that Discord. Also, any chat message that you send on DataStax pages, that probably actually goes to us. So
Yeah.
if you need to reach out, we're available.
Hmm.
Great. Okay. Yeah, thanks again for your time. That was a really fun hour. I hope everyone has a good rest of your day. And
Hmm.
again, let us know if anything interesting comes up. I had so much fun
Yeah.
today. Take care.
Same here. Have a good one, y'all. See ya.